Okay, students, let us start. Okay. So we were talking about NTU method, and we have seen what is effectiveness, is it not? So we have seen what is effectiveness. Okay, effectiveness is actual rate of heat transfer divided by maximum possible rate of heat transfer. Correct. Now, in case we have seen two things there, right? Now, in case if I say first case was MC MH dot C M dot H or MH dot CH is less than MC dot CC. Now, in case of heat capacity case where the heat capacity, if M dot H CH is less than M dot C CC, then then effectiveness can be equal to Q by Q max. I can always write this as this effectiveness. I can write it as M dot HCH divided by TH1 minus TH2. Eh, Observe here, this one is TH1 minus TC1. You see that? The maximum difference, is it not? Now here in this case, what I can write, I can say divide by, what is the minimum here? Minimum is M dot H CH into, we can have TH1 minus TC1, right? So this can cancel, and I can have TH1 minus TH2 divided by TH1 minus TC. So in this case, epsilon can be equal to TH1 minus TH2. Write it along with me, students. There's nothing great here. TH1 minus TC1 when M dot HCH is less than M dot CC. Right, this is the next equation. What is the equation now? Till now we have written, we have got till 19 here. Okay. After 19, write this as 20. Write this as 20. Okay, effectiveness, and write this as 21. 21. Okay. Also, if M dot CC is less than M dot HCH, then then epsilon is equal to Q by Q max, which is equal to M dot CC into TC1 minus TC2 divided by M dot CC into TH1 minus TC1. Correct? So this can be written as TC1 minus TC2 divided by TH1 minus TC1. Makes sense? So here epsilon is equal to TC1 minus TC2 divided by TH1 minus TC1 when M dot CC is less than M dot HCH. Right, this is 22. This is equation number. Easy. ಆಯ್ತಾ? So ಇದ್ರಲ್ಲಿ ನೋಡಿ, you can understand this here. See, this is the, see, when you compare here, you have two things, TH1 minus TH2 and TC1 minus TC2. In these both cases, which is bigger in this, in these both, which is bigger for this case? The bigger one is TH1 minus TH2, is it not? Why? Because m dot HCH is lesser. When m dot HCH is lesser, that means you have a higher temperature difference for hot fluid, because hot fluid has a lesser m dot C. Correct. Now here in this case, the same thing, TH1 minus TH2, TC1 minus TC2. In these both, which is bigger? Bigger is this. Higher difference is the second one. So what is happening here? In general, what we can write? We can write the larger of the temperature difference divided by maximum temperature difference. That way also we can write the effectiveness. This is very important in problem solving. They might give you the four temperatures and the m dot C values, and they will ask you what is the effectiveness of the heat exchanger. If you want to calculate effective heat only on the temperature, you can decide. Or they might give the four temperatures and they will say the cold fluid will have, has a lower heat capacity, m dot C. Cold fluid has the lower m dot C. When the cold fluid has lower m dot C, what should happen? TC1 minus TC2 should be on the numerator. Denominator is the same for both, which is TH1 minus TC1. So only if the temperatures are given, you can know the effectiveness. M dot C is also not required. Only information is required is M dot C, is it greater for the hot fluid or is it greater for the cold fluid? Or if, whether it is smaller, which is smaller? The smaller of the m dot C will have the larger of the temperature difference. Make sense? I hope it's making sense. Okay. Now, next point. So, effectiveness, 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 eta can also be defined as eta is equal to delta T L divided by delta T maximum. What happened here? ಯಾವುದ್ರಲ್ಲಿ? Hmm. TC1 ಮತ್ತು ಇಲ್ಲ, highest difference ಇಲ್ಲಿ ಆಗುತ್ತೆ. Maximum difference ಇಲ್ಲಿ ಇದರಲ್ಲಿ ನೋಡಿ, you get the things right. So largest difference will what happen? What you mean by largest temperature difference it can have? It is TH1 minus TC1. A fluid can undergo the largest temperature difference that a fluid can undergo. It is either TH1 minus TC1. Here also TH1 minus TC1. Both the cases. This is the maximum temperature difference a fluid can undergo. Whether it is cold fluid or hot fluid, we don't know. Passing in, for coming in and going out. What is the largest temperature difference it can have? That gives the maximum rate of heat transfer. Or when will the maximum heat transfer in the heat exchanger happen? When one of the fluids, okay, maybe if it is a hot cold fluid reaches the hot fluid reaches the C1 temperature when it is coming out. If the cold fluid, hot fluid reaches to the cold fluid entrance point, okay, the temperature of the cold fluid entry, that is the maximum possible heat transfer. Or the cold fluid goes to the hot fluid entrance. When the cold fluid reaches the temperature of the hot fluid entry temperature, which is very difficult. If it is an infinitely big heat exchanger, only then this will happen. Otherwise, there will be always a difference, is it not? So that is the maximum possible to the limit. And how do you decide that? What is that? Here you have to see which one is going the difference. Whether hot fluid is making the difference, is going through that difference, or the cold fluid is going through that difference. If m dot HCH is lesser, then hot fluid is going that distance. Make sense? The temperature change, which is from TH1 to TC1, either hot fluid can have or cold fluid can have. Which one will have? Which has a lesser heat capacity rate, I will say. Got the point? Clear? Very important that we make that insight. That cannot happen later on. Don't say, sir, ಈಗ ಅರ್ಥ ಆಗಿಲ್ಲ ಮತ್ತೆ ಅರ್ಥ ಮಾಡ್ಕೋತೀನಿ ಸರ್, ಆಗಲ್ಲ. ಈಗ ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಳಿಲ್ಲ ಅಂದ್ರೆ ನೆಕ್ಸ್ಟ್ ಟೈಮ್ ಅದನ್ನು ಕಷ್ಟ ಅಂತ ಬಿಡೋದೆ. ಹೌದಾ ಅಲ್ವಾ? ಅದು ಆಗಲ್ಲ ಸರ್, ಅದು ಕಷ್ಟ ಉಂಟು ಸರ್, ಆಗಲ್ಲ. ನಮ್ಮ ಯಾರು ಸರಿ ಟೆಕ್ಸ್ಟ್ ಬುಕ್ ಎಲ್ಲ ಇಟ್ಕೊಂಡು ಕೂತ್ಕೊಳ್ತಾರೆ. That is the mindset we have. Yes or no, you tell me. Yes or no? ಒಂದ್ಸತಿ ಕ್ಲಾಸಲ್ಲಿ ಅರ್ಥ ಆಗಿಲ್ಲ, ನನಗೆ ಅರ್ಥ ಆಗಿಲ್ಲ ಅಂತ ಲೆಕ್ಕ. ಕ್ಲಾಸಲ್ಲಿ ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಳಿ. Understanding the class, students. Okay? Sure. Next. So now, effectiveness epsilon can be written as delta TL, where delta TL is the larger of the temperature difference TH1 minus TH2 and TC1 minus TC2, and delta T maximum is always equal to TH1 minus TC. Very, very important to understand. This question may come. This time it will come. I'll tell you. I have a prediction. This time a question will come where they have given the entrance and the exit temperatures of both the fluids, and they say cold fluid has lower m dot C than the hot, or hot fluid has lower m dot C than the cold. And people will say, sir, ಏನು ಕೊಟ್ಟಿದ್ದಾರೆ ಸರ್, ಹೇಗೆ ಕಾನ್ಸೆಪ್ಚುಯಲ್ ಕೊಟ್ಟಿದ್ದಾರೆ. और मनोज सर से, सर इस बार कॉन्सेप्चुअल दिया है, मुश्किल है. अरे कॉन्सेप्चुअल कहाँ मुश्किल है, समझ लो उसको. कॉन्सेप्चुअल दिया है तो आसान है. आपको तो पहले करना है कॉन्सेप्ट समझना, उसके बाद प्रॉब्लम्स करना. आप कॉन्सेप्ट ही नहीं समझते हो और धड़ाधड़ प्रॉब्लम बनाते बनाते जाते हो, क्या उससे क्या मिलेगा? आपको नहीं मिलेगा. इसे इंजीनियर्स भी अच्छे नहीं होंगे, है कि नहीं? Done. Next, the heat capacity ratio. Write it along with me, students. The heat capacity ratio. In Nagade, he has given it as R. In our Senjal, he has given C. Okay, it's okay, whatever be the case. R is defined as R is equal to m dot C minimum divided by m dot c maximum, which can be written as capital C minimum, capital C maximum. It can be anything. That is, if m dot, write this as equation number of where we have this is 23, this is 24. Now I'll write it here so that I'll get more space. If m dot hch is less than m dot cc, then r is equal to m dot hch divided by m dot cc. Okay, this is equation number 25. If m dot cc is less than m dot hch, then r is equal to m dot cc divided by m dot hch. This you write it as 26. Very important to understand these things. Very easy. Easy also. Once we do that, you will see how easy it is. And the value of note, the value of or the values of epsilon and r ranges from 0 to 1. Very important. Ranges from 0 to 1. I'm purposefully taking more time because afterwards you don't understand. Is it so? Huh? Ah, yeah. Open art survey. Oh, good. I concentrate on the concepts only, students. I don't concentrate on the problem. Problem is yours. I'll do problems, obviously, but then you have to solve more and more problems. That's why I say now this time I cannot give you more problems because I don't have a big team. I'm only one. Okay, and others are there to take classes, but I need to build a team later on. Okay, so uh, once that comes, we'll get more problems. Okay, but now that's why I tell you to take other institutes. You say problem series, get materials. Okay. So my strength now is not material. Somebody asked it from some. I don't know who asked. You people only told yesterday. If they ask anybody, I think yesterday Bharat said that. They first ask what is material. A material ಕೊಡ್ತಾರಾ? They don't worry about thinking, teaching. They worry about materials being given. Okay. Which to materials. If you give this big materials, the coaching institute is very good. So next time we'll have it. We have to have it with nice colored materials. When you see it, only the things should get interest. ಎಲ್ಲ ಟೈಪ್ ಕಲರ್ ಎಲ್ಲ ಯೂಸ್ ಮಾಡಿ ಚಂದ ಮಾಡಿ ಗ್ಲಾಸಿ ಪ್ರಿಂಟ್ ಮಾಡಿ ಮೆಟೀರಿಯಲ್ಸ್ ಕಮ್ಮಿ ಇದ್ರು ಕೂಡ ನೋಡುವಾಗ ಖುಷಿ ಆಗ್ಬೇಕು. ಚಾರ್ಟ್ಸ್ ಎಲ್ಲ ಇಟ್ಟು ಚಂದ ಚಾರ್ಟ್ಸ್ ಕಲರ್ ಚಾರ್ಟ್ ಮಾಡುವ ಆಯ್ತಾ. ಕರೆಕ್ಟ್ ಆಗೋ. ನೆಕ್ಸ್ಟ್ ಈಗ ಪ್ಯಾರಲಲ್ ಫ್ಲೋ ಅರೇಂಜ್ಮೆಂಟ್. Parallel flow. Okay. So now, uh, see, generally what happens is parallel flow arrangement. So if you consider the parallel flow arrangement, how does the parallel flow arrangement goes? it goes from th1 to th2, right? And then tc1 to tc2, correct? This is the range. Fine. So now, in general, we can write. See, observe. We write if you consider LMTD. Okay, if you consider LMTD, see what did we derive in LMTD? If you see here, just remember this. Let us remember this one. Okay, or I copy it. I don't want. Okay, it's becoming very poor. Let me go here. So this equation we have not written anything. Is it for 12? Okay, 12 we'll take. We'll take 12. Okay, this is LMTD here, and we are saying equation 12. Okay, now equation 12 can be written as equation 12 can be written as equation 12 can be written as log of log of equation 12 can be written as log of log. I'll write here like this: th1 minus tc2 divided by. Can I write that? Or LMTD in general, I can write it as LMTD also, is it not? Okay, let th1 minus th2, right? Let me write, okay. So this is th1 minus uh, tc. Oh no, sorry. This is not. Yeah. TC2, I'm sorry, TH2 minus TC2 and TH1 minus TC1 can be written as UA into, I will write mu P. Let this be equation number 27, right? 27, where mu P is equal to 1 by m dot C Cc minus 1 by m dot H Ch, right? So this can be written as log of delta T1 or delta T2 divided by uh, oh no, wait a minute, let me write this as H only. We'll have minus there. So because there is no minus there, we put, okay, that is, yeah, minus. Let us H, let us write this H, let us write this as C. One correction, students, C, and then there let be minus, because minus is very useful. Let there be a minus. Okay, with mu p is this. I tried to bring in that mu p here. Okay, so minus is very important. Fine. So now we can write delta T2 in divided by delta T1 is equal to minus UA into mu P. Fine. ಸರಿಯಾ ಯಾವ್ದು ದೊಡ್ಡದು ಯಾವ್ದು ಚಿಕ್ಕದು ಅಂತ ಗೊತ್ತಿಲ್ಲ ನನಗೆ ಹೌದು. So I can write this as log of this one, if you say delta T2 by delta T1 is equal to e power minus mu a, so u a mu p. Correct now? Further going, I can write 1 minus delta T2 by delta T1 is equal to 1 minus e power minus ua mu p. It should be plus. Mu p should be the other way around. This is plus. One second, one second. Yeah. It is plus. I'm very sorry. It's plus. Correct. It is plus, not minus. Plus. And there is a minus here. Correct. So there is a minus. So plus or minus. It's correct. Right. So now this is the case. Okay. Go slow. Okay. Give a let there be a lag phase shift between what I say and what you write. A small phase shift now. Okay. This is fine. Okay. Now further going, I can write this as. mm, I can write it as delta T1 minus delta T2 divided by delta T1 is equal to 1 minus e power minus UA into mu p. Or I'll write it as, I can write this as further TH1 minus TC1 minus TH2 plus TC2 divided by TH1 minus TC1 is equal to 1 minus e power minus UA mu p. Fine. Okay. Write this as equation number 28. TC2 here, no, TC2 minus TC2. This one should be TC2 minus TC1 because TC2 is bigger, TC1 is smaller. Correct. Change it, students. This is TC2 minus TC1. This is my bad. TC2 minus TC1 because the fluid will undergo higher, the it should be positive basically. It cannot get a negative value. Okay, that's correct. Change it. ಸೊ ಅದು ಇಂಟ್ಯೂಟಿವ್ಲಿ ಆಗಿ ನಿಮ್ಗೆ ಗೊತ್ತಿರುತ್ತೆ ಅಂದ್ರೆ ಒಮ್ಮೊಮ್ಮೆ ಮಿಸ್ಟೇಕ್ ಆದರೆ ಅದು ಆಮೇಲೆ ಒಂದು ಕ್ವಶನ್ ಮಾರ್ಕ್ ಬರುತ್ತೆ ಆಮೇಲೆ ಈಗಪ್ಪ ಇದು ಬಂತು ಅಂತ ನಾನು ಬರ್ದಿದ್ದ ತಪ್ಪ ಸರ್ ಮಾಡಿದ ತಪ್ಪ ಏನಂತ ಗೊತ್ತಾಗಲ್ಲ ಆಯ್ತಾ ಸರಿ ಇದು ಬರ್ತಾಯ್ತಾ ಚಂದ ಮಾಡಿ ಬರೀ ಇದಲ್ಲಿ ಸ್ಟ್ರಗಲ್ ಇದು ಡೋಂಟ್ ಹ್ಯಾವ್ ಟು ರಶ್ ಇನ್ ಟು ದಿಸ್ I think tomorrow today evening also we will make exchanges okay problems okay this will be completing now ಏನಾಯ್ತು ಆಯ್ತಾ clear ಸರಿ ಈಗ now if I consider what is epsilon let say let m dot h ch be less than m dot c cc let is the case then 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 th1 minus th2 would be th1 minus th2 would be greater than tc2 minus tc1 correct so epsilon would be equal to th1 minus th2 divided by th1 minus tc1 and r would be equal to tc2 minus tc1 divided by th1 minus th2 which can also be equal to m dot h ch divided by m dot c cc. I can have that also. Okay. R can also be like that. Where is R? We do see MC minimum by MC max. This is the actual case, is it not? So that can be equal to the temperature difference as well. Correct. It can be Tc2 minus Tc1. Here you see the other way around. And Th1 minus Th2. The other way around. Make sense? So given that, now you can write equation 28 can be written as th1 minus th2 plus tc2 minus tc1 divided by th1 minus th2 divided by epsilon. How can we write this epsilon? How did this epsilon come? Just observe here. th1 minus th2, then tc2 minus tc1. Here th1 minus tc1 is there. Instead of that, I have substituted th1 minus th2 divided by epsilon. You are comfortable with that? Okay. That should be equal to 1 minus e power minus u a mu t. Correct? Now this can be written as epsilon into 1 plus 1 plus tc2 minus tc1 divided by th1 minus th2 is equal to 1 minus exponent of minus u a 1 by m dot h ch plus 1 by m dot c cc. Correct? Fine till here. Now let us take m dot hch outside. Okay. And what is this? This one is R, observe. This one is R. This particular thing is R. And when you take m dot h ch, this will also be R. How did I write Tc1 minus Tc2? See here. What is R here? R is MC minimum by MC max, right? So where C is more, the yeah, if I consider like that, okay. So can I write? Okay, like, how did the question is? How did you write? So if I say Q, Q is the same, is it not? Q is equal to m dot h ch into th1 minus th2, that is equal to m dot c cc into tc2 minus tc1, right? Now if I write m dot h by mc, that should be equal to th1 by this one, is it not the other way around? I'll repeat it. Wait, I'll give you more. See, the reason is, the question is how did we write this, is it not? Let us see. So are you clear with the thing that m dot h ch into th1 minus th2 should be equal to m dot c cc into tc2 minus tc1, correct? Yes, no, because that both are q1, that is the amount of heat transfer which is happening. Now I'll write m dot h by ch divided by m dot c cc can be what? Tc2 minus tc1 divided by th1 minus th2. Yes or no? Write it, write it, don't worry. It does not flash sometimes. Sometimes I assume that you know, but that may not be always the case. See, there are slow learners, and slow learners do a lot of miracles. This is what was told by Ashok Junjunwala. Ashok Junjunwala was not is a professor in electrical department in IIT Madras. He says that the people who come from private engineering colleges, they are slow thinkers. They're slow thinkers, but they're consistent. Unlike the B.Tech, who are not consistent, wants everything instant. These people put efforts for a longer duration of time. Because of the efforts being put and the longer duration of time, they come up with very nice technologies. It's about persistence rather than excellence in the short period of time. It's a marathon. It's not a sprint. People think it is a sprint. No, it's not a sprint. Sprint is what we are doing for this our gate. This is sprint. We are running 100-meter race. But then developing technology is a marathon. And for that, generally, he says the people from the private engineering colleges who have not cleared JE, they are generally good in this. That's what he says, as per his experience. Okay. Because of the more amount of efforts being put, consistent efforts being put. Okay. Sure. Done? This is done. Now this can come as, I can write epsilon is equal to epsilon into 1 plus r can be equal to 1 minus exponent of minus u no, ua divided by m dot h ch. into 1 plus m dot h ch divided by m dot c cc. What is m dot h ch by m dot c cc? It's r again. So what I can, epsilon into 1 plus r is equal to 1 minus exponent of this particular thing, ua by m dot hch is called ntu. So this is called, this is minus ntu, minus ntu into, this is minimum of both, okay, this is minimum of 1 plus r, 1 plus r. So I can say where ntu is equal to ua by m dot c minimum. Here m dot h was minimum, m dot hch was minimum. So you have to take the minimum in that. Important. Equation number, last one was 28. So let us go with this as 29 students. You go this as 29 because sometimes that is used. Okay. That was not used till now, is it not? Hmm? And let us go with this as 30. Let us go with this as equation number 30. Okay. Now epsilon for parallel flow, PF means parallel flow, can be given as 1 minus e power minus of ntu into 1 plus r. Write it neatly, student, because this is very important. Divided by nt, sorry, 1 plus r. What is ntu? ntu, this is 31. ntu means number of transfer units. What transfer? Heat transfer units. It stands for number of transfer units. Very important. What is number of transfer units? It is UA. UA is amount of, it is heat transfer coefficient into area divided by MC minimum. Now this actually gives how big the heat exchanger we need. And here what we are using? We are using only properties of the fluid, and as also m dot and property of the fluid. We require what is minimum, we have to require, we can know that. Okay. So okay. NTU, very important. NTU gives the measure, NTU gives the measure of the size of the heat exchanger. Very, very important. This gives the measure of the size of the heat exchanger. Bigger the size, bigger the NTU. This can come as a question. Okay. So what is the use here? How does this simplify things? It simplify things in the sense that, okay, when you consider, I'll tell you that in a moment. Okay, it depends on how much what you say heat transfer is required. Okay, that gives a measure how big it is. It's fixed now. So next, calculating the other one becomes very easy. Okay, we will see the examples. Okay. Done. the size depending on the requirement in terms of number of transfer units. Here you are not saying A, okay, you are saying NTU is a measure of how big it should be. I'll come back to that. I'll tell you this one after a minute. Similarly, another point is if it is a counter flow for, I'm not going to do the derivation, I'm going to just write, okay, for a counter flow heat exchanger. In NAG, the derivation is done. Okay, you can see refer PK NAG, PK NAG, or derivation of counter flow arrangement. Okay, fine. So for counter flow heat exchanger, epsilon, which is the effectiveness counter flow, comes as 1 minus e power minus NTU into 1 minus R divided by 1 minus R divided by 1 minus R into e power minus NTU into 1 minus R. These two are very important, students. You have to remember these equations, okay? It's required that you remember this 31 as well as 32. These both you have to remember. Exactly. R into e power NTU into 1 minus R. So here, how it is easing the things. Let us see how it's easing the things. Okay. See, uh, to find okay how NTU helps in design. Let us say. Okay. Done here. Fine. How does NTU help in design? How does NTU epsilon NTU method is helpful in designing or selecting a heat exchanger. A heat exchanger. Okay. First step one.
So,
Yes, please.
so for counter flows, the effectiveness and R will be same.
Or
Counter flows.
yes, NTU and R is the same. NTU and R is the same for counter flow as well as parallel flow. Effectiveness is same. It's no difference. Effectiveness, to say equation, which is this effectiveness is given as this. Is it not? That does not change. Okay. R does not change. NTU does not change. NTU is here. Three things. What is NTU? UA by M dot C minimum. Any doubts? Give me some time. Revise again. Once more. See. Once more, see, one see. I'll give you 2 minutes so that percolate. Just revise for a few minutes. From
So
the we have started, we have said what is effectiveness. Any doubts here?
so what if heat capacity of cold fluid is less than hot fluid?
Then that would be cold fluid will be MC smallest. So NTU has to be defined by whatever the minimum is.
The whole formula will change over there.
No, it does not change. It remains the same. You can
So
check
heat
it out.
capa-
If you consider
there is
parallel flow, wait a minute. Yeah, tell me.
m dot c is less than that thing. M dot f.
See here, what we have taken now is we have taken m dot h is lesser than m dot c. Had we taken the other way around, let us do it. You will get the same equation. Let me do it in yellow because not yellow will be very purple. Okay. Now, had you written m dot c c c is less than m dot h c h, then what this would become? This would become Tc2 minus Tc1 divided by Th1 minus Tc1, right? Okay, and what this would be? This would be equal to R would be equal to Th2 minus Th1 divided by Tc2 minus Tc1. Uh, Th1 minus Th2. Th1 minus Th2 and Tc2, which would be equal to m dot h, instead of m dot h is m dot c cc divided by m dot h ch. Correct? And this would be, instead of writing like this, I would write this as Tc2 minus Tc1 plus Th1 minus Th2 divided by epsilon has changed, so I will write Tc2 minus Tc1 by epsilon. Make sense? And this would come out as Th1 minus Th2 divided by Tc2 minus Tc1 plus 1. See the beauty? Correct? So this is R plus 1, no change. And what would come out from here is, you would, instead of taking m dot hch out, you will take m dot cc out. And what you will get, m dot c here, you will get it as, this side you will get it as, okay, 1 minus exponential of minus ua divided by m dot cc into m dot h ch, sorry, m dot yeah, you will get, what was this side, it was m dot c and c, is it not? So you will have m dot c, yeah, so you will have this as m dot ccc divided by m dot h ch plus 1. Convinced Agachya?
Yes, sir.
Well, so it would remain the same. That's why C minimum is important. M dot C minimum. It is not H or C, whatever the minimum is. Clear? No doubts. Similar thing would happen with counter. Now let us see how the things goes. So let us see the step one. Step one would be, okay, to find exit temperatures. Exit temperatures. Okay. If m dot c cc is less than m dot h ch, then r would be equal to m dot c cc divided by m dot h ch, and NTU would be equal to U naught A naught by M dot C C C. Can be calculated. R calculated. R calculated. We know all those things, is it not? We can calculate it. Okay. Now, from from this information, from this information, from this information, epsilon PF or epsilon CF is obtained. Effectiveness is obtained. Okay? And since effectiveness is equal to delta TL divided by TH minus TH1 minus TC1, this would be equal to TC2 minus TC1 divided by TH1 minus TC1, right? So from this obtained from 30, from which equations? From 31 or 32? From 31 and 32. And from this obtain TC2. Problem was TC2 as well as TH2 was unknown. In LMTD that was the problem, is it not? TC2 as well as TH2 was unknown. So here after doing this, we can calculate what is TC2. Once we calculate TC2, TH2 can be calculated. Correct. TC1 is known, TC1 is known, TH1 is known, you can calculate TC2. Fine. Okay. Or this is option one. Instead of step one, let us say option one. Right? Let's option to find exit temperature. Okay. Change it instead of step, you say option. Okay, option. Fine. So now, after this, after TC2 is known, we can always calculate TH2. TH2 can be determined using m dot HCH into TH1 minus TH2 is equal to m dot CCC into TC2 minus TC. So you have calculated that. That is one side. Now another thing. Option B. Option B. To determine surface area, the surface areas given given m dot H CH m dot C CC TH1 TC1 U naught and TH2 TH2 sorry TC2, I'm sorry, this is TC2, there's a mistake. Yeah, TC2. If we know this T cold or TC, okay, even we can determine we can determine TH2 from m dot HCH into TH1 minus TH2 is equal to m dot CCC into TC2 minus TC1. Correct? If one is given, okay, the other can be calculated. If the other is given, the first one can be calculated. So one of the exit temperature is given. Okay. Now we have to find out the surface area. Okay. Now if m dot m dot H CH is less than m dot CC or TH1 minus TH2 is less greater than TC2 minus TC1 TC2 minus TC1, then R is equal to m dot HCH divided by m dot CCC, and epsilon is equal to TH1 minus TH2 divided by TH1 minus TC2, right? So from equation 31 and 32, NTU is determined, and from this we can determine surface area. We can determine surface area. Don't worry, this complicated won't come. I've just told you to, all these things have been told to get the idea. Tomorrow you have to go to the industry and this is coming. So you should have the basic idea. That's heat in heat exchanger. These are only two methods. There are different things like you have to find out U naught. U naught, for that you have to do calculation. Sometimes nowadays it's all CFD. Okay, they use CFD to calculate U naught. Once U naught is calculated using computational fluid dynamics, then these things are because U naught calculating is not that easy, and that you increase the heat transfer rates. So there are various methods that are employed, and things are really complicated in this. But this is a basic thing. The complication is only in calculating the heat transfer coefficient. Other things are easy, simple. Heat transfer coefficient either has to be done through experiments. It's always an iterative process. Okay? So, which one counter flow? See, counter flow is always better. This we cannot. See, counter flow is always better than parallel flow. Okay? So generally we go with counter flow only. Okay? But there might be some applications. I don't know where there is slow heating or slow cooling which is required. Rate of generally in chemical reactions. Maybe I'm just imagining. I don't know the application properly, where parallel flow is preferred over. Maybe when the rates of heat transfer has to be slow, then maybe, or the flow directions is constant. You cannot change it. It's if one place it's coming, the other place is coming. It has to go in that direction. You cannot do anything else. Then maybe. Now the special cases. Special cases. Special cases. Okay. First one. When one of the when one of fluids are undergoing phase change, if one of the fluids are undergoing phase change, then what? Then m dot c large is equal to infinity, and r, which is equal to m dot c small divided by m dot c large, becomes equal to, that is delta t small divided by delta t large, sorry, delta t, yes, or delta t large by delta t small. Delta t small by delta t large, is it not? Is the small by large? Mm-hmm. Okay, okay, see, you have to understand this. Delta t small corresponds to m dot c large. Delta t small corresponds to m dot c large, and delta t large corresponds to m dot c small. So it's proper. So if this is a cold fluid, then this is the cold fluid. This is the hot fluid. This is the hot fluid. It's correct. Just think about it. Okay. This will go to 0, and and epsilon parallel flow becomes equal to 1 minus exponent of minus NPU. Just see that if R is equal to 0, then what happens? 1 plus R, it becomes 1. 1 plus R becomes 1. This has been asked a number of times. This is a favorite for GATE. Okay. So another one, because it's easy, it can be asked. Okay, another one. Epsilon counterflow also becomes equal to 1 minus exponent of minus NTU. Both same. So write this as equation number This is very, very important in gate perspective. 32 is over. Let us say this is 33 and 34. Important for gate. Done? Done. Second case. Case 2. Case 2. When m dot c h is equal to m dot c, then if that is the case, r becomes equal to m dot c small by m dot c large is equal to 1. Whatever be the case, right? So now for epsilon parallel flow, this becomes equal to 1 minus exponent of minus 2 times NTU, because 1 plus R, 1 plus 1 equals 2, divided by 2. This you write it in the next equation 34, 35. So let this be 30. And epsilon for counter flow becomes equal to NTU divided by 1 plus NTU. I'm not doing the derivation for this. For derivation, refer now. Okay, it's an easy derivation, but still. Okay, so these two important for gate. Gate generally these are the questions which they ask. Important for you. So theory complete. What is required now in heat exchanger is evening we will have problems. Fine. Which one? Yes. Then you go as a. It does not become 0 by 0. It is 0 by 0. No. 1 minus 1 becomes 0, right? 1. It becomes indeterminate. So you have to go with the other method. The derivation is given here. It becomes indeterminate, obviously. Hmm. So there is a procedure given there. They calculate NTO in a different fashion. Okay. So then they apply and then you get that thing. Okay. NTO is done in a different fashion. You'll see that. Okay. So I'll stop it here. Okay. But this is very, 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 very important. Okay. Okay. Huh? Heat exchanger theory is done. Now we have to do only problems. All the basic, only thing is the two derivation I did not do, but that is okay. Okay. Not required. Derivation is not required for gate, but then I go give it for your understanding. Huh? Finish. Problems only I'll give. Heat exchanger is finishing today, and tomorrow we'll start with radiation. I wanted to finish here now, but sometimes what happens?